它是整体上分析。
我们开始上课。So I saw a few new students join the course. So let me review what we learned last week. So in last lecture, I explained why we need the motivation to study this subject. We also spend some time to review two important ingredients as a preparation to learn this subject. One is, of course, special relativity. We particularly reviewed how to obtain the Lorentz transformation of Lorentz group. We also explained the end of the week's course of the compounds. Harmonic oscillator. As a reminder to think of the exercise, the compounds these dynamic objects. And also, it's extremely important to understand how the quantize fields. Okay. That's the subject of the lecture weeks. Okay. So, do you have any questions about what we learned last week? So I upload this lecture notes to e-learning, so you can read it. There could be some errors, so when you read it, please be careful. And yeah, as said last time, I wish we can discuss more in this class in real time. So if you have any questions, please interrupt as many as you want. So today, the subject we want to start with again some background material for quantum field series is called classic field series. So this is of course not quite a new subject to you guys because you have already learned a lot with many examples, right? As we mentioned last time, Maxwell field is a very familiar example of classic field theory. The goal of this course is basically to learn how to quantize it. So before that, let's first review or learn some background materials, how to understand the classic field series. Okay, and this is also very important because I remember last time there's one question from students: what are the constraint conditions to construct field series? When we learn this subject, we essentially learn how to construct Lagrangian action field. Right? To quantize it, we have to understand which kind of theory we're going to deal with. What are the constraints to construct this kind of theory? So this is the and what are the key properties? If you learn even in the classical level this theory, what are the key properties? Sometimes these properties are preserved even after you quantize it. Okay, then you'll be very good, right? You don't need to do more than you can, you can go through. So classic field theory, maybe perhaps the most familiar formulation. To tell somebody what is which kind of what is the formulation of classical field theory is the Lagrangian formulation. Indeed, if you want to specify field theory or classical field theory, in particular, if you want to specify the dynamics. And the dynamics of fields, okay? Only know which field is not enough, right? You have to know the dynamics, right? And the dynamics of a field is specified with what? Where it's usually by Lagrangian. And regularity is, for example, as we learned in the classical mechanics, using this capital L. Capital L. You learned in classical mechanics, the capital L is it's a function of what? The function of Q dot, and also T. Remember that? Okay. So similarly, if you want to find the Lagrangian of a field, then this has to be a function of phi, right? As we explained last time, we basically treat phi as the field theory as the basic variable. Okay, phi. Phi itself is also a function of x and t. Okay? Then you can also depend on phi dot. Okay, phi dot. Similar as Q dot. Of course, what's the time? That's difficult. Then, so this is only the time derivative, okay? As you can expect, you can also depend on the special derivative. Special derivative of phi. And if you consider the theory should be relativistic, okay, or Lorentz invariant, then the time and the space will play very much equal role. Okay, so we can just write this like that. Write this as some view. So in this sense, we can construct the so-called Lagrangian this way. So capital T as a function of capital L as a function of T, and we write as the integral over space, and we use a kerning to denote the Lagrangian density. Use a kerning L to denote the Lagrangian density, and then do this space integral. Okay. So what this really means is, again, the picture is some kind of lattice. Okay, you think about the field theory has many infinite degrees of freedom. Okay, you lattice it, then this x becomes some index. Just label the degrees of freedom. Okay? When we consider in the viewpoint of classical mechanics, indeed you can do that. Think about the classical mechanics with infinite number of degrees of freedom. You have to sum over this index, x index, then you get the precisely the same Lagrangian as what you learn in classical mechanics. Okay, that's why this is the reason why we cook up some new this kerning L, which is the Lagrangian density. The Lagrangian density is a function of phi. Okay. Okay, very similar to classical mechanics, right? So with this Lagrangian, you can write down the action. In T, you know, action is a time integral of the Lagrangian, and the space integral. And with the kerning L, which is Lagrangian density, we quite often just combine these two. As that, in particular in the relativistic case, we don't distinguish between with T and X. I can write it as force is a Lagrangian density. Okay. This is what usually happens. Okay. But this is a little bit too quick, right? Or you may ask me, how do you know? Why do you repeat the L is only function of phi, function mu phi, not some more complicated like second derivative, okay? Partial, something like that. Yeah. Do you think there's some constraint behind this result, right? Behind this result. So, when you think about the Locality, why this is so, it's because again, because there are similar constraints in classical mechanics. Okay, so you can ask yourself, whenever we have, the point is, whenever we face a new problem, you have to go back to your familiar. You should ask the same question in classical mechanics. Why in classical mechanics you don't have some Lagrangian dependent on Q, for example, Q double dot? What is the reason for that? Why in classical mechanics we don't have our Lagrangian dependent on Q double dot, for example? Only Q dot. What is the reason? The reason is, if you have a Lagrangian dependent on Q double dot, then when you derive your equation of motion from this Lagrangian, okay, you will have some third derivative, time derivative, okay. You see it? This means what? This means when you try to find the solution for the equation of motion, you not only need the initial position and the velocity, you need something more information, okay? Which is certainly go beyond Newton's law, okay? Newton's law tells us the only initial or initial condition I have to specify is the position and my initial velocity, and I can predict all the trajectory. Is that right? Not further, okay? But if you go beyond this, certainly you go beyond this usual understanding of classic mechanics. This is the reason. Okay. So similarly here. Okay. All that in classic mechanics, L ends only on Q loss, but not, for example, some higher node. Okay. I remember last time there's one question asked some higher node. It's a very good question. So we'll come to this question. So for the same reason, we also restrict our Lagrange density in the field theory, curly L, depending restricted to L depending only on phi and phi dot, but not phi dot. Okay. Okay. Now, with Lorentz invariance, this essentially means, as I said, you don't distinguish much between time and space. So it just means they're only dependent. Phi, partial short, okay, but not higher derivatives. Not higher derivatives. Okay. Oh, of course, you can challenge this claim. Okay, you can just say, I mean, why this is essential? I can drop it. Okay, I can go beyond Lorentz invariance system. I can go beyond, for example, there are some effective field theory describing some materials. Okay, you can go to some non-relativistic regime. Okay, then you drop this restriction. Then you have to distinguish time and space. Okay? Depends on which property you require. What we're talking about. Okay, so we will come back to this. Yeah, we will discuss a lot. We're essentially now try to focus on this locality constraint field theory. Okay, and we will see it. Okay, we see it. If you go beyond this, if you drop this Lorentz invariance, indeed, you should treat the time derivative and space derivative separately. Okay, even though you require the time derivative, which is the dot, you cannot go beyond the double dot. Okay. Right? Sorry, you can go beyond the single dot in your Lagrange density, but indeed you can go for the space derivative. You can go. Okay, it's fine if you drop the Lorentz invariance. Okay. So, do you have any question about why we restrict ourselves onto only this form of Lagrange? So sometimes we don't distinguish Lagrange density or Lagrange just because we don't want to sample compensation. Sometimes we also call this Lagrange. Yes.
说中文，就是从洛伦兹对称性的角度的话，它那个叫什么？ 偏微分的话，就那个什么 phi mu 西塔，它的话就是说它作为一个变量，它是就是什么是每个 mu 是一个，还是它们是一起的？嗯，怎么说这是？
You mean the mu index?
对，
Yeah, of course, you can see here, from here. Of course, mu run from, for example, 0 to 3, 0, 1, 2, 3. They represent the independent variables. Okay. Whenever mu here just means there is a bunch of variables.
就我意思就是，如果它是跟 mu 的那个相关的话，那它是否还是一个论变量？无限的表示。
Okay, very good question. So eventually we will see that this saying the variables is phi, function mu phi doesn't mean that. Okay, very good question. Essentially, we will see in order to construct the Lorentz invariant Lagrange density, this mu index has to be contracted. Yeah, that's a very good question. Any other question?
那个拉丝密度为什么是没有，就是时间的函数为什么？就它为什么没有显含那个时间？就那个拉丝密度里
It
面，
depends time. I just skip it. Was example communication. Any other question? It depends on time.
Maybe sometimes the Lagrangian is directly depend on time. For example, a classical driven oscillator, it may contains a cosine omega t factor that, which is not contained in phi.
Okay. I see the question. Is that the same question for you? Yeah, I think in principle you can, but this we're okay. We'll go step by step. You will see how to restrict which kind of Lagrangian density we're going to focus on.
For example, can we eliminate the time factor by using the special, for example, picture transformation to a time independent picture, and we can just treat a time independent Lagrangian.
Okay, the quick answer is I think it depends. It can depend on time. At this moment, maybe in this course, we're only focusing on some very simple examples. For example, if your field theory system has a particular source, okay, then it certainly will depend on time, because the source can provide some very designed dynamics, some maybe time dependent, some random force or something like that. Yeah, you can cook up such a system. It certainly then depends on time. But here, yeah, or later, we just focus on very simple examples. We skip those complicated examples. So it can depend on time. It's something. Yeah. Any other question? Okay. Yeah, that's a very good question. See, because later we will pay much attention, spend a lot of time today to discuss the symmetry. Okay. Then if you consider more complicated, for example, my field theory has some source. Okay. Then mostly you break a lot of symmetries. Okay. You break a lot of symmetries. For example, translation symmetry. Okay. If your source is sitting here, not staying some, homogeneously, right? It's staying in some particular position, then the system lost the translation symmetry. Okay. So we know which kind of Lagrangian should be written or constructed. Then from this Lagrangian, we also learned in classical mechanics. From this Lagrangian, we can try to derive this equation motion. Okay? Equation motion. And the equation motion, by definition, equation motion governs the dynamics. Tells you how the field should evolve. Okay. Okay. That's the meaning of the equation motion. So how to get this one? We have to do this familiar trick derivation, which is from the we have to do variation. Okay, variation. If the point is from what we learned from classical mechanics, we know to find the equation of motion following this so-called least action principle. Okay. Okay. The equation of motion should let this action, if you change the trajectory, for example, okay, in your classical mechanics, if you do a small variation of your trajectory, the change of the action should be always there, okay? If you do a small change, that's what we learned. So this is the variation principle. Here, you do the similar thing. For example, we do now the variation for the fields, okay? And we demand to find the equation of motion, we demand that under this small change, this delta S should always zero, okay? Okay? This principle decide the equation of motion or can derive, okay, following this principle, least action principle. Then we can get the equation of motion. Okay, we can get the equation of motion. So let's carry on this one. This was a here. So let's do this calculation. So delta S, everything meaning is very clear, right? Delta S is just the responding change of the action under this small change, okay, of your fields, okay? Now the point is your fields is some function, right? Often, okay? The variation of these fields means you do this arbitrary small change, okay? Arbitrary small change, okay? So delta S, what is delta S? So how should we work it out? We do calculate this small change of S. Yeah. So so suppose if I have a bunch of different fields, let me use a small a to denote in case there are any fields. So we can do this variation because the Lagrangian density is also a function of the fields. So we just do this derivative. And as said, in the case of Lagrangian, we treat the phi and the partial mu phi are independent variables. Okay? Okay? We treat these as independent. So we should treat them independent. So we should get something like this. Okay? This is your variation of your action. Now we want to do a small trick to deal with this second term. There's a second term. Because you see, in second term, there is a combination of there are two actions, right? There is a partial mu acting on this phi field. See, there's also a variation which is delta. Okay. Now I'm allowed to exchange the order. So this is equals to partial mu and delta. Okay. Delta and partial mu equals to partial mu and delta. Okay. Because they're quite independent. One is figure the ordinary derivative, another is the variation. See? Now, because of this, then you can see there is a derivative. There is a derivative acting on delta phi. See, and there is another term. I can try to add another derivative, which is the derivative only acting on the first, not the second. Then I can form or combine them together. I can have a total derivative. See? Why we like a total derivative? because there's an integral. You see, if you have a total derivative plus this integral, then this entire integration becomes surface or boundary, right? This is total derivative, like what you did in your first year. Then you get only the boundary term, right? Let's do this, okay? So, which means this equals to, mine with another term is equal to this is what I said, essentially, okay? Because I want to add to the second term, so let me subtract first, okay? To make this same. So you see, I now I could have the total derivative. The derivative means for this times this one. Okay. Okay. Then subtract this term, you get this term. Okay. You get this. See? Now let's first look at this total derivative, because total derivative is plus an integral is very simple. Okay, as said, it becomes some boundary terms. So this term, after this integral, essentially goes to some boundary terms. Boundary term means what? Means just to evaluate this. Just to evaluate this at the boundary. Okay, the boundary. The boundary, right? Because it's total derivative. You see, it becomes a simple boundary. Then the question is how to deal with those boundary terms, right? We cannot simply just throw it away, right? No. Okay, we cannot simply just throw it away. Now the point is there is a choice to make it to be trivial. Okay, or you can forget it in under some condition. For example, since you are now trying to evaluate both this object times this object at your boundary, okay? Suppose your system has a boundary, okay? Now try to understand what is the meaning of this delta phi. Delta phi is a small change of phi, right? Now if you restrict yourself, say, or choose some boundary condition, say delta phi always equal to 0 at the boundary. Then this term vanish, right? This term vanish. Because you don't allow the phi have a small change at your boundary. Okay? You only allow phi has a small change in the block. Okay? Suppose your system has a block in the boundary. That means we fix a particular boundary condition. If you fix your value of phi, at your boundary, this is called the deletion boundary condition. Learn that in your mathematical method of physics. You learned that this is deletion boundary condition, right? This is deletion boundary condition. Now, alternatively, you can choose another boundary condition, which is this one. This partial L, partial mu phi, okay, is equal to 0 at your boundary. Then you can also forget about this because this is A times B, right? Either you choose A equals 0 or B equals 0. This always both are trivial, right? So this is called the Newman boundary condition. Okay. We will see later, very soon actually. This object is nothing but conjugated momentum. You see. So if you consider phi as your variable, then the conjugate variable is essentially the partial L, partial mu phi. Okay. So this looks like the position. Then this looks like position variable. That's what you learned in your classical mechanics. Okay, I'm trying to make an analogy with your classical mechanics. Okay, to understand it. So this means this looks like a position variable. Then this is like a momentum. Okay, because they conjugate with each other. So if you choose this delta phi because there at the boundary, this is the initial boundary condition. If you choose this is zero at the boundary, this is Newman boundary. Two boundary conditions. But the point is, both boundary condition guarantee you can forget about this one. Okay? Is the contribution comes from the boundary. You choose a boundary condition to clear this or let this vanish. Okay, vanish on the boundary. Yeah, that's the point. Now. Then the boundary condition guarantees this is zero. Then there's only term left over is the first, is this part. Okay. Now, as said, the list of action principle says that for any small change of phi, delta S should be zero. Okay. Then, which means this coefficient has to be zero, right? Otherwise, it's not possible. Right? Because for any small change of phi, it will always be zero, which means this is zero. So this equals to zero is essentially the equation of motion. This is what we want. The equation of motion. Okay. So we get this equation of motion by doing this variation of the angle. Okay. Are there any questions for how to derive the equation of motion? Okay, good. Now this is a Lagrangian formulation of classical field theory. Okay. But as you may learn the classical mechanical course, there's another formulation. There's another formulation. This is not the only one, right? There's another formulation. What is that? Anybody? Yeah. What is another formulation of classical mechanics? What is that?
Hamiltonian.
Very good. Very good. Okay, that's the subject. Next. Hamiltonian formulation for Hamiltonian. So, what is it? What is this? So now we already started from the Lagrangian, so it's better to transfer from Lagrangian to Hamiltonian, right? Right. So in that sense, again, remember in your classical mechanical course, in order to do that, we can try to first define the momentum, right, or canonical momentum. You learned it before, okay? P is defined as the partial L, partial Q dot. In your classical mechanics, remember that? This is the P. Then you can get your Hamiltonian H. H will be equal to PQ dot minus L. The formula you have many degrees of freedom to sum over it together. Okay. So this is essentially the way to go from Lagrangian to Hamiltonian, right? So in Hamiltonian formalism, instead of consider Q and Q dot are independent variables, we consider P and Q. Remember that? We consider P and Q are independent variables. Okay. We can also, under this formulation, to write the equation of motion, right? There's just a independent formulation of the same system. Now the point is we want to generalize this to the field theory, right? We have to do a little bit of work. Okay, how to do that? So that's not very hard actually. So let's do it. So I will just so since we are now we know this L. Let's just go through precisely follow the procedure in quantum mechanics. We know this L, right? Then we can define the P, right? Just following this one. We know phi is the Q, right? We know phi is the Q. So we can define the P. P is again the part, even in field theory, is the partial L, partial phi dot. Yeah. Right? Because as I said, we know how to get the Lagrange in classical physics. When you have a Lagrange, when you have your Q dot variable, which is essentially phi dot in your field theory, then following the formula, you get P.
这边被黑板挡住了，
Sorry?
被讲台挡住了。
Ah. Okay, good. You see? You see? No? Okay. So work it out. So this is partial phi dot. Let me brief about the rotation phi dot. And L is what? Let me write it. This is the dy integral with the Lagrange density with the variable phi and phi dot. Okay. We can just work it out. So how to do this one? How to do this one? That's not difficult actually, because you can view this integral as a sum. Okay, as a sum. As that, the special coordinate can be viewed as the index. So essentially, partial phi dot sum over y L, which is density phi dot dy. Okay. Now this is a sum over y, and this is a, let me put the index here. This is about the derivative for the x. Okay. This is about the derivative x. So essentially, only when you do this kind of derivative, you only pick out this x position. So you'll get partial L, partial phi dot x. Now you get your P, right? You get your P. Okay. You get your P. Then this is the flow volume, and you can define something called the momentum density, which is inside that box. You can define something called momentum density, which is times t. Partial phi dot. Okay. So this is the momentum density. Momentum density. So now we know the variable in field theory and the conjugate momentum. And then we know how to write down the Hamiltonian. Like what we do here, which. So H H is PQ dot minus L, okay? H is PQ dot minus L. So H equals to, as I said, there's the index sum. E phi dot, okay? And L. It's a field theory. And then you take continuum limit. You take continuum limit. This becomes the integral. It becomes integral. And inside the integral, there will be pi. We just define pi dot minus kernel, which is Lagrangian density. Okay. Then naturally you can view this as your Hamiltonian density. Okay. Your Hamiltonian density. This is my Lagrangian density. And this is the momentum density. And this is the very size the level. Okay. Efficient. So you might say this is a little bit abstract. In fact, this can be worked out very precisely for an example. So let's look at an example. So if I consider the simplest free scalar fields with the Lagrangian density L equals to half pi dot squared minus up gravity by square. So now I'm trying to look at the simplest free scalar theory, and this is the Lagrangian. Okay, let me just tell you this is Lagrangian, and following this Lagrangian, we can derive the equation of motion. We can also derive this Hamiltonian. Okay, and also this conjugate momentum. Work it out. So what is the equation of motion for this free scalar fields? I just now try to write the separately with time derivative and space derivative. Because why? Because in the Hamiltonian formalism, and if I want to work on in the Hamiltonian formalism, essentially I distinguish time and space. You see? But in Lagrangian, it's not necessary. You see? In Lagrangian, everything is covariant. You can see the question asked earlier is when we you can also write, for example, you can also write this as partial phi, partial phi as the new index. So in Lagrangian formalism, everything is covariant. Covariant meaning we don't distinguish between time and space. But Hamiltonian formalism, from the very beginning, even to define this momentum, we have to take the derivative with respect to q dot. Dot essentially is only time derivative, so we have to distinguish. Okay, that's the reason. So what is the equation of motion? So from here, we just introduced how to get the equation of motion, right? Only this equation. Get the equation of motion. Okay. So what is the equation of motion? Also, Lagrangian. So the following formula, you will get the equation of motion is nothing but the partial t squared minus partial x squared plus m squared. For example, we consider the mass. This will be my equation of motion, okay? And m is the mass. So in Lagrangian, the m squared, phi squared is the so-called mass term. So-called mass term. So you do the variation, or you don't need to do variation anymore. Just following the box formula, you can derive the equation of motion. This equation of motion, as said, can also be made as the covariant form, which is the partial mu plus m squared phi equals to 0. Familiar one? Is it familiar one?
Like,
That's right. This is the again the Klein-Gordon equation, but with completely different interpretation, right? With the previous Klein-Gordon. Okay? Phi is no more some wave function in quantum mechanics. Okay, phi is a field. Phi is a field. So now Klein-Gordon equation appear again in a different interpretation. It appeared again as equation motion for a free scalar field. As the equation motion. Now some people are even very lazy. Okay, they want to introduce some very funny symbol to use the box. So quite often when you read the papers or textbook, you will also see some form looks like this. So essentially, this one, same thing. Okay? Different notation. Some people like this to use a box symbol. Okay. So as said, for this example, just 1 minute, you can work out what is the variable in the Hamiltonian formulation. Okay, for this theory, just following those formulas. So first, what is the canonic momentum? The canonic momentum in this case will be the phi square. Okay. That's the phi square. Sorry, phi dot. That's the phi dot. Why? Because you take a derivative with respect to phi dot. Right? Phi dot. There's only one term sensitive to that, which is here, phi dot square. Okay? You take the derivative with respect to phi dot. There's a square to cancel with these two. So only one phi dot. So pi is phi dot. So pi is phi dot. And what about h? H is the integral. Inside this integral is so-called Hamiltonian density. Hamiltonian density is given by this pi dot minus L. Okay? Pi dot minus L. So what is that? Pi is this one, right? Yes. So work it out by yourself and you get this. Okay, so this is the pi dot minus L inside this integral. This is the Hamiltonian. And you can go further because we introduced the equation of motion in the Lagrangian formulation. But as you know, in Hamiltonian language, how to write the equation of motion? Can anybody see how to write the equation of motion in Hamiltonian? Yes. How to write down the equation of motion using Hamiltonian?
P equals partial Hamiltonian and gravitational.
Very good. Very good. Okay. So we have to, yeah, that's perfect. That's correct. So another way to say this is we have to use something called a Poisson bracket. No? Does anybody who didn't hear about what is Poisson bracket? Everybody knows, right? Know what is a Poisson bracket? It's the same thing as what he just said, right? You can express the Hamiltonian equation in terms of Poisson bracket. Okay, why we like this Poisson bracket? Because essentially for canonic quantization, right? Okay, if you do further, you want to quantize your system. Just replace your Poisson bracket by Dirac bracket. That's it. Or commutators. Okay, and that's it. So what is the Poisson bracket? want to write the critical motion component only then. But bottom bracket, let me remind you, so in the classic mechanics course, you should learn something. So for the bottom bracket, given two functions, f and g, bottom bracket is the bracket, right? The bracket. Act on f and g in this particular way. It's a partial f, partial q, I, partial g, partial p, minus partial f, partial p, partial g, partial q. Is that familiar to you? Yes? Okay, so simply define this way. This is the definition of this bracket. No fancy things. So this is what we learned in classical mechanics. So from this, you can easily check, for example, the Q and P bracket will be equal to, just plug in, okay? Plug in this. This will be equal to the sum I delta AI times delta L I minus 0 to 0. If you want to calculate it, see? Then this is delta times delta KL, okay? So PQ bottom bracket equals to delta, you see? Or equals to 1. K equals to L, okay? Now, similarly, in field theory, you can do this. Okay, you can do this, just following these steps. Okay, that generalize a little bit, not much. Because as I said, essentially the field theory is the infinite degree of freedom in classical mechanics. Okay. Right, as we derived in the first course, in the first lecture, if you have a chain of oscillators, okay, in the continuum limit, you get the field theory. So the Hamiltonian formulation for fields is quite similar to classical mechanics. One can also define for the bottom bracket that use capital F and G. This will be defined as the integral, say partial F, partial phi, partial G, partial pi. Using Hamiltonian formulation, we knew the phi and the pi variables. Partial F, partial pi, partial G. Okay. Just do this one, and with the integral, because as said, you have to sum over all these degrees of freedom. The x looks like an index. So this is the bottom bracket. Now you can also easily check the commutator. For example, phi commutator with pi. So the bottom bracket phi pi, this will be equals to, you will find the function of phi is the function of x, also t, but here nothing to do with t, it's only if the t. Oh my god, let me write pi. Why? We want this one, then we'll get it from delta function, okay? Similarly, there, right? There, and you can write the equation of motion. As he just mentioned, in Hamiltonian language, the equation of motion is the q dot equals to a partial h, a partial p. Okay? Then in this field theory variable, then this equation of motion will just become phi dot equals to open bracket phi means h, okay, which is nothing but partial h partial pi. Okay, partial h partial pi, and pi dot. Another piece is the pi dot is the minus partial h partial phi. So this is the equation of motion in Hamiltonian language for field theory. As said, for that particular example, we worked this out very precisely. Okay? Then you can convince yourself. Indeed, it makes sense. For example, examples. Examples. This equation of motion in the case of free scalar field theory, this will become the first one becomes phi dot equals to pi, and the second one becomes phi dot equals to the okay. Now you combine these two equations, you see clearly it's equivalent to this equation. You see, that's correct. See? Because in this case, pi just looks like some intermediate variable. Okay, you can eliminate this pi, combine these two equations. So everything is consistent. Everything is consistent. The convenience for this Hamiltonian language is because of later when you do quantization, you just replace the bottom bracket with 1 over I h bar with a commutator. Then you're done. Okay? That's the convenience of this. We will discuss this in great detail next week. Not today. Okay. So are there any questions about this Hamiltonian formulation of the classical field theory?
在那个拉格朗日量密度那里，它是对那个四维时空积分，但是到这里的话，它又是对那个。
No, Lagrange density there's no integral. Lagrange has integral. Lagrange density is the density. Density has no space-time integral. Density.
但这里它是对三维空间。
That's right. It's reasonable, right? Because Hamiltonian is defined as some time slice, no? Hamiltonian does not include the time interval. You see?
但是它后面有一个拉格朗日量，这个拉格朗日量你又表示成拉格朗日量密度。
No, that's density. That's again.
但是在之前讲的拉格朗日量密度里面，它是对四维时空积分之后成为拉格朗日量，这里是对三维时空积分、三维空间积分它成。
No. L, capital L is a function of t. Remember that action is action there is a time. Any other question?
对，那个是应该差不多的问题，就是在之前那个拉格朗日密度是写成 phi 和那个是 partial mu phi 的函数，但这里就写成了 phi 和 phi dot， 这个是为啥？
因为他们这样不是轮变的。
That's right. That's the short answer. Very good. Yes.
也就
To
两
emphasize, in Hamiltonian formula, we treat time and space different.
就是他们这样里面时间这个变量有特殊的意味。
Okay.
你就算把它写成了 phi 的形式，它依然是只对时间做这个，只对时间这一项做。
So the Lagrangian over here, and the Lagrangian before have different forms.
它是它是连成，
Can you do it again? Here is the curly. This is the capital L. I believe capital L. Capital L. However, this is the curly L. It's a different thing. Okay? This is the density.
Oh.
Okay. They're different L. Okay. I try to distinguish them. Any other question? This is also density, of course, is inside the input. Any more questions about the Hamiltonian formulation? Okay, very good. Now, next topic we're going to discuss is some very interesting property of the sphere theory. So far, we just talk about different language, how to formulate it, right? We haven't touched some more deep physics or what is the key property of this kind of field theory. Which kind of field theory looks good? Which kind of field theory looks bad? Or, So this is about this topic is actually very important. We want to single it out and spend some time to discuss this. So we call it locality. Okay. Locality. It's again related to the question asked last week. I already wrote. So if you we have some examples, right? We have some examples here. We know how the equation motion looks like. For example, for a very simple field theory, right? This is the equation motion. Now you ask yourself the question, what is the general property of what is the general property for this equation motion or field theory? Okay. Can the equation motion become very general differential equation? Can any type of differential equation be viewed as an equation motion? Okay. Ask yourself that kind of question. So this is the topic over here. So if you think it about carefully, then you realize that the equation motion, at least all the fundamental fields, equation motions can only contain fields and also derivatives at the single point, at the same point. Not 2 points, you see? It's a differential equation, right? Often it's a differential equation, but the point is this differential equation is only associated with 1 point. Okay? It's not some differential equation looks like some acting here related to some acting there, okay? Or associated with some x and also y. No. The equation motion only associated with a single point. You can take here. By single point, I literally mean the single space point, okay? Because when you talk about the locality, we only focus on space, okay? If you talk about some 2 points in this time direction, we don't call it the locality quite often, okay? Not just by definition. Locality, what do you mean by locality? Locality means you localize here, right? Localize at a point, okay? That means locality, okay? So if you observe all these familiar equation motions, think about it carefully, you realize this property. Look, it may be at first glance it may be trivial, but it's actually highly non-trivial. Highly non-trivial. You realize all these familiar fundamental equation motion for the fundamental field are local, or as differential equation is including the fields or maybe its derivatives, but the point is all about a single point, okay? All about a single point. So the best way to illustrate this property is just looking at the examples. Okay? That example we already showed there. Okay. The next famous example is the maximum equations. Okay. If you still remember the maximum equations, see. All about a single point, you can check yourself. Okay. It never appears some term acting on some point x related to with some other point as y. Okay, no. Okay. No. And perhaps another example, first example I said shows there. Another the third example is the Einstein's equation. Einstein's equation is the variable is like G mu nu xt. Okay, G mu nu xt. G mu nu is the tensor. Okay, we introduced the tensor last week. Not quite tensor field, but this is a typical tensor field. Here you can see it with 2 index. Okay, with a 2 tensor index. Okay, and there's a function which based on time. We describe the symmetric of the space time. So this equation is also local. Check us out. Okay, and also there's a famous equation for the Dirac equation. And they associate the variable the numerical field, and the equation motion is I'm not trying to go into details, say how to understand how to derive those equations. I'm just showing this as a fundamental equation to govern the nature of our world. They are all local as examples. Okay, they are all local. Okay. Now this is the level of equation motion. Now you ask yourself the following immediately another question, which is this is the equation motion, but what about the lambda, right? What about Lagrange? So because of this restriction for equation of motion, then there must be some restriction for your Lagrange. You cannot write down some Lagrange arbitrarily. Claim this is a good field theory Lagrange. No. Okay, there's a strong relation with locality. So locality also implies the Lagrange density. Lagrange density can only depend on the value of the fields. And the at a single point. At a single point. This means what? Since Lagrange density, Lagrange is the integral of the Lagrange density, right? The integral is the space integral, okay? Okay? The integral is the space integral. Lagrange density can only depend on those variables at a single point. It essentially means that there can only be one space integral in front of the Lagrange density, okay? Cannot have two, okay? Is that clear? Because this is the object inside can only depend on a single point. Right? That means there can only appear a single space variable, okay? X, not be Y. Okay? So this essentially means, so why we get this restriction, you can easily, you can easily check. For example, you can give an inverse proof. For example, if your Lagrange density depends on X and also Y, okay, and also Y, then equation of motion follows from the derivative for this Lagrange, right? Then you can easily get some equation of motion, not only for fields or derivatives at a single point, right? Right? So this result comes from there. And this essentially means the locality forbids or does not allow some terms look like this. For example, my Lagrange, I have a double space integral. And with some fields, for example, looks like this. This is not so far, we only have some very general observation. Okay, we get some lesson from these known examples or familiar examples. But you could ask yourself a more deep question. Essentially, why? Why we need this restriction? Okay, what is the origin for this restriction? You can ask yourself. Then you go back to history. Okay, just check what other people are thinking. Okay, you go back to history. Then you find that the concept of the field was first invented, essentially want to preserve this locality. Remember that? So this in history, this happens around 1830. Okay. Around this age or year. And this guy called Faraday, right? Faraday first invented the concept of the fields. Because he doesn't like something non-local, okay? Some interaction just immediately happens between this point and that point. He doesn't like that. Okay, he believes that there are always a fields. Okay, there are always a field. All the physical effect should propagate just locally from this point to all the points surrounding this point, and then propagating this way through the fields to another point. Okay, it doesn't believe there is immediately interact or effect propagated from this point to that point. Okay? So actually, that's the reason to invent this concept of the fields. That's amazing, right? That essentially means what? It essentially means that from the very beginning, the fields was invented to preserve locality or implement locality. Okay, so like locality is some very, very natural property of field theory. Okay, because field theory was invented to preserve that. Look, okay, that's what happened in history. Not the reverse. In history, in order to preserve locality, people invented the concept of the fields. Now we want to come back. When we introduce the fields, we want to understand better why locality, what is locality, why we should have locality, why locality is always there. Right? That is partially the reason. Okay. Let's have a break and we'll continue in 15 minutes.
你说他的这个你不有在，他不能说话就让两个点之间距离的他就这样说了，因为这是我在 x 这个点对物联方向那边在相当于就。对，直接看这个推动都直接推动必须要和那个点的中间，我必须要有一个找，但是我不能在那点找，对，在那点是扰动只在扰动周围，扰动作用为什么道具好，这个不是要去对，这么一段它就可以就和这个和是给它在这儿有影响，和另一地方可以产生就这一个部分。如果说应该是不是在可以重复就一块了，因为它那个大块，这个防御和我的方程和这个六个字，可以看到那个一点的那个脑部电梯这个就是是一个某个地方，从的到从大家看，这个这看电视，我看这个电梯，没想到如果大概是两个，现在是 经历任何事情，
就是一个另外一个比较精准的话来说，三个方面的那个讲然后这个这个还说的是对，然后其中核心概念是可以说可以这个大家查资料的话，基本上都是的 classic concept。就是把这个事情的社交两个体系啊，对，进行就是这个好，我都是这样这套这个这个好，这个 stay 里面还有一个 response。但是它这个也是蛮长的，然后然后面说话然后这个我也是就是这个例子我也是，还有那维平面旋转做这个是我也可能它这个第四对吧？我这个是一个状态，就相当于旋转吧，应该是通过旋转，然后再到了这个极的把一撇，然后用坐标表示，这个是这个分量，这个是显示量是必然，这是这个矩阵。
你把你学习
然后这个的写学上80第二句就你相当于是个转值，爽一点，然后那个长难题比较爽。现在的转值整体的这个正交的，但它的just bad。
划得出一个
没有，然后
上次的图，因为它文章大，
向量的然后但特别是标量保持这个不变，一点就是具有真实运动。
前面那个高法怎么样？
反正可以各种各种
自己背后，
但是要注意，看这个事实光明，这边这个弯弯这边能够感觉自己的这个这个环境整体为什么？我在看啊，我都知道，我以为
对，算重视
这边的落一下，那咱们两提到一方减券是吗？减出来吗？好，是这个第一个。哇，这个什么？非常的明白，看得到一个情况。然后。然后那个因为年都在弄，就看他这个这样，就他的这个可能是略小觉悟，这个我们给定这个地方，对，然后就开始说就构成了一个 Lorentz。所以需要注意，这个是合理的 Lorentz 传送位，没有你我知道在思议的还行，你就是标量是我看到可以两个水衡标有关，应该是连续变化，还是其中连续变化，但是抽数里面有些东西比散了，然后很多下面外部然后复合相当于半个来到对方半个三角形，是这样。有这样实在这两个外方，就是每个这个字啊，用然后不是说这个孔变的在这个算翻出来，它就上看。相互说，应该难以，它是光这个是慢这个可以，但是都是连续的，时间反也 但它也不是两个，所以这难度还是容易，但是心肺正这个加重扣的，我这昨天的没看到。
来晚了，狗子的
密度大的
前面
非得是点上实时拍，经常只有画面，
而且会上，而且你发现课间
就是觉得。我因为真大都是这种量的，
那黑衣服，
就那个，
那这么说也行。
对，我要发在视频里这个。
对，用眼看就是我发弹幕锐体，为了后续它 graphics 有些这是吧？这就是都没错，太
共识判阅，就他上节课讲的第二章，
我研究的那个，研究上面的，哎，我看你你就不偏心，对，自己光天给有，自己的讲完我理解，还有这个就是这不行，我觉得别想着干，和上的一样，真的该怎么讲，我一直到。找不到最迟到，奇怪这个样子，你说这个有意思，这么准，你要不就别去，真的不行。他们去不是，对，那种我还有，这个要解读，一般都是更细讲对这完事，但是正常去，对，你能参与还可以，这个人可以啊。
你有你问题。
你有客户听到的，
不光来说可以，那也不能太那个了吧？估计还要6。说实话，及格就行。这么多题，没想到非常有及格就一点。如果你跟我要是及格不一的，我这个要对预判球员，哎，你们这分离不玩手，这个人重要的啊，就是因为你要把这个你要这个就看，那你这个坏了，那以后还把那个种吧，现在还要把这个不能少拿点东西，这因为发上那个这样的这样的就有这样的。这个球我个人太不熟，所以我就不太清楚了。可能是外界和卷皮带的。以前有这种习惯，是哥哥这个东西，我那这个真是这样子啊，没有这种。就是我是觉得有关这个这个是我认为。不是，就是就感觉他就刚觉得，结果我自然不 PPT 这种，我应该是说的很多，还是那基本上不加，我有这个理解。你到我打一方就是有点是，当时不能这个搞完了看你们写在哪？
Okay, let's continue. So we discussed the locality of the field theory. So through the equation motion, we can see the locality essentially means the some points in the space or space-time can only affect the nearby points. Okay? They cannot affect some faraway points. Okay? Because these are the local differential equations. Okay? Differential equation means the points can only affect nearby points, and then slowly propagating these effects. We cannot jump. It has to be local, not jump. So back to the higher derivative question. We mentioned in the beginning of today's course, we also come back to that question because now we essentially introduced the notion of locality. You can check yourself. If you only allow some higher derivative for the space part, not time, okay? As said in the beginning, if you introduce the higher derivative for time derivative, then you have trouble, right? You basically violate the familiar law of the word. Okay. But now, if you only allow the higher derivative for the space, x derivative, then you can check. You can preserve locality, right? Because locality is only about you act at this single point. Okay. And you can at this single point you can add the higher space derivatives in your Lagrangian or equation motion, perhaps. Doesn't violate locality first of all, okay? But it certainly go beyond the Lorentz invariance, right, as you can imagine. Okay. Because Lorentz invariance guaranteed that whatever you do for t, and you have to do for x, or whatever you do at x, whatever you do for t, right? Because they play the equal role. If you drop this Lorentz invariance, then you can, okay? You can cook up, construct some theory with the higher derivative, but point is only for x, not for t. Okay. So that's a bit of clarification. So, do you have any question about this locality property of the field theory? Yeah, I wish you can ask many questions. Okay, so like the topic we want to discuss is the symmetry. This is a big chapter, right? This is the big chapter. So we only have like less than 1 hour to discuss this topic. This is an extremely important thing in field theory, actually. So this is a topic. This subject is about symmetry. Because we already introduced the formulation of classical field theory, we can now talk about symmetry. Okay. Before quantization, okay. Before quantization, we can talk about symmetry. To discuss this symmetry, we have to mention we want to avoid this famous female mathematical physicist called Leather. We're going to discuss Leather theory. So Leather theory is actually Leather theory is about discuss continuous. So So what do we mean by continuous symmetry? We introduced in last week, right? This Lorentz group. See, there are 6 parameters. There are 6 parameters to parameterize 3 rotations plus 3 boosts, right? Whenever you see this transformation was implemented by some object with some continuous parameters, this means this symmetry is a continuous symmetry. Is that clear? Very easy, right? Okay. If somebody tells you one symmetry, just let him write down the transformation, okay? See, just look at the transformation. If there are some continuous parameters, this means the symmetry is a continuous symmetry. Yeah, that's what we mean by continuous symmetry, okay? No fancy meaning, just simply this way. Now, we also introduced last time, there's some discrete symmetries. Remember that? Like P and T, right? So parity is a typical one. It's a discrete symmetry. Time reversal is also a discrete, right? These are the discrete. So for discrete symmetries, of course, distinguished from continuous symmetry. There's no continuous parameter, okay? Today, we're going to focus on continuous symmetry. Okay? We're going to focus on continuous symmetry. And we also want to derive the letter theorem. This is an extremely important topic, even for those people who are doing research nowadays in quantum field theory. This is a very, very, very modern subject, okay? Even up to now, people are still trying to understand what is the best understanding of this letter theorem. Okay? What is the best tool we have to use to formulate this letter theorem, okay? And people even invented or developed, discovered new things out of there, okay? Okay, just in recent years, okay. To be clear, okay? So if you want to do some research associated with symmetry in quantum field theory, pay attention to this. This is always the starting point. So we talk about the symmetry. We'll also talk about the field theory. So it's better to clarify how the fields transform under symmetry transformation. Right? What do we mean by a symmetry? Essentially, how do you define in which case you think you observe some symmetry in field theory? Right? It's better to give the definition very clear. Okay, what do we mean by symmetry? So sometimes this is confusing. By the way, it's a confusing concept, right? Sometimes when people talk about symmetry, it can mean many different things, okay? Many different things. That causes confusion, right? So it's better to be sharply clear and what we're talking about. Okay. So let's define the symmetry in field theory in this way, okay? In the following way. So consider continuous transformation. On the field. For example, phi. We always use phi, but not necessarily to be really a scalar, right? Keep in mind, just to refer to a generic fields. To be schematic, just use phi, okay? So for given field, if there is a continual transformation on this field, okay? And again, this is another place could cause confusion, okay? What do we mean by a transformation on the field? Okay? Sometimes the people talk about the coordinate transformation, okay? Sometimes the people are talking about the transformation on the fields, but what is how they are related, okay? What is the best way to understand or to distinguish, okay? That could cause confusion. Now, since this is a continuous transformation on the fields, and then there exists some infinitesimal form, right? Because the transformation associated with the continuous parameter. Whenever there is a continuous parameter, I can make this parameter to be very small, right? Like epsilon, okay? Okay? That's guaranteed, right? Because it's continuous. Which, in infinitesimal form, can be written as I always prefer, in order to clarify, to avoid any confusing, I prefer to write the transformation to send something to another thing. Okay, this should be very clear. Right? The transformation means you transform from A to B, right? Send A to B. Okay, that's what transform does. Now we're talking about the transformation on the fields. Okay, we're not talking about the coordinate transformation, to be clear. Okay? Sometimes coordinate transformation doesn't do much. Okay? But transformation on the fields is really physical. Okay. Because you transform the fields. I give you a fields configuration, you can transform. Okay. For example, you can translate it. Okay. You can rotate it. Okay. That's a very physical implementation. Okay. So here, the transformation on the field means you send some object to another object as that. So we send this field to another field, but we want to focus on the same position. Then we can write this form. You can write this form. As you can see, I avoid this shift of the coordinate. Okay, you see, I keep everywhere x. You see, I don't use some s prime in order to avoid the confusing. Okay. This means I really transform my fields, right? I transform my fields. Now, the point is any small transformation or the continuous transformation in some infinitesimal form means you transform your field by a small amount, right? That's by definition, right? Then you can always write the object after transformation can be expressed in terms of the one before transformation, okay? Plus some small amount, right? Right? You can always do that. Check yourself, okay? Any continuous deformation, you can always do, okay? Then this form is kind of cheap. Let me explain again. This means the one after transformation, this is before transformation. Since this is the infinitesimal amount transformation, they can only differ by a small amount. Let's use this alpha as a small parameter. Okay, alpha is a parameter. It's a small. Alpha is very small. And what is delta? Alpha should appear here, right? Naturally, right? Because alpha is like epsilon. Okay. So what is delta? Delta means some operator. For example, derivative. Okay. Delta means some operator acting on phi. Okay. Okay. That's you can also imagine, right? Right? Like a Taylor expansion, if you want, very roughly. Okay. You see? Right? When you do Taylor expansion, you have many subleadings in terms of derivatives or higher derivatives. You see? That derivative means your differential operator acting on your original function, right? That times some small a parameter, then you sum over all this, and you can try to estimate or approximate your original or your function before transformation. Okay. Is that clear? This is the term, the meaning of those terms. Even though this is a simple expression, but it leaves some explanation. So let me make it very clear. Okay. This is some field or some function if you want. And this means that it happens some transformation act on this one. Okay. Then the transformation to another one. Send it to the new one, because of the infinitesimal amount, can be expressed in terms of the previous one plus some small parameter times something. This something can be expressed always, okay? Expressed as some operator acting on the original function. Okay? Okay? That's what it is. So if you accept this one, then you can do a lot of things. Okay? You can do a lot of things. Now, first of all, let me finish the definition about the symmetry. So the symmetry means if the field transform in this way, Okay. Alpha is a infinitesimal parameter. And delta is the deformation. Of the fields. If this transformation leave the action invariant, then we call it this is the symmetry or continuous symmetry. There is a symmetry, or it is implement, or it means the transformation. Okay, be clear. The transformation represent or implement symmetries. If it leaves the action warrant. Okay. Okay, this is a one-line definition. But I hope this is a short definition. Just means there are some transformation action of the field, then the action does not change. Okay. Whenever it happens, it defines a symmetry. Defines a continuous symmetry, because this is the infinitesimal transformation. So because the action is invariant, then what happened for the Lagrangian density? That's what you can ask. Because the action is expressed as a four-dimensional integral of the Lagrangian density. Okay. So if action is invariant, at the most, the Lagrangian density can transform up to a total derivative. Is that clear? Okay. The action is dx4 over the Lagrangian, right? Right. So this is the invariant, which means this one, L, at most can transform up to a total derivative. This is the total derivative for the index to the factor mu that we use another J mu here. For some J mu. Is that clear? This result or this consequence is the result of the definition of the symmetry. Okay. If it is a symmetry, let's use it. Let's explore what's the consequence if there is a symmetry. If it is a symmetry, S is invariant, because S is the integral over L. So L at most can transform. At most can transform up to this term. Okay. Of course, this can be 0. Okay. J can be 0. L does not change. S is of course not change. Okay. It's a perfect. It's a good symmetry. That's fine. I'm saying now at most. Okay. At most it means that this can be 0, but it can also be non-zero. And also you can transform in this way. If you transform in this way, it guarantees S is invariant. Okay, because this is the total derivative. Now after the integral again, it becomes some boundary terms. Now we assume the boundary contribution are trivial. Okay, we assume boundary contribution are trivial. Then this is the most general way for the L if there is a symmetry. Okay. Now, as said, this result comes from a symmetry. Okay, a symmetry indicates this one. But there is also another way to work out what is the what is the amount of L transform? You see? So a few minutes ago, we introduced how to derive the equation of motion by doing variation, okay, following the least action principle. Right? Means we do a arbitrary small change for phi. We demand delta S is 0, okay? Then we get the equation of motion. Remember that? This is a little bit similar but different, okay? You see, here we introduce another small change, okay? We also see that this is a small parameter, then this is a small change, okay? This is also a small change, but just expressed in another form. Fine, physically it's also a small change, okay? Now, of course, not an arbitrary small change can represent a symmetry, right? As you can imagine, right? If you do an arbitrary small change of your fields, most probably you get nothing, okay? Most probably you get nothing. But I'm saying now, if this is a symmetry, if this is a small change that S is invariant, then you define the symmetry. Then you can imagine that this kind of small change is not the arbitrary small change, okay? Maybe it's some particular. It's better to be some particular small change. Yeah, that's one thing I want to clarify. Apart from that, everything is the same as before. There's some particular small change. If you want, we can denote this as some particular small change using some delta with a hat. Okay, hat means some particular one. Doesn't mean some arbitrary one. Okay. Now, following the previous variation principle, since we know how phi changed, because this is the way phi changed, there's a small change, we can derive under this change how the Lagrangian changed, for example, or action changed. Okay. This is like a first principle. Let's follow you, because my action is constructed from my fields. Okay. If I know how my field changes, in principle, I can derive how my action changes. Okay. In this case, both are small changes. Now, combined with another property, if that change really represents a symmetry, then I have two results. Okay, one is from I just follow the like what we derived from equation of motion. I can get some small change of the Lagrangian, and if it's a symmetry, we know the Lagrangian has to be changed in this way at most. Then we get two results for this changes of Lagrangian. They have to be equal, right? And we get some equation. Okay. So that's the idea to derive Lerner's theorem. So out of this equation, we can get something called conserved current. So this is the core of the Lerner's theorem. So so this is just the words. Let me finish that. This step by step. So on the other hand, we know L changes under this change, this delta hat of phi. Okay, under this change, we know how it changed. For example, we know delta L, like what we did in the derivation of equation of motion, it can be expressed partial phi, the small change phi plus partial L, partial mu phi, a partial mu, small change, right? Small change, okay? Small change. See? Now this one is defined in this way. You just plug this one, plug in here. Yeah. Plug in here. And again, we choose to cook up some total derivative. Okay, we have some total derivative. So this equals to We want some total derivative. Means let me do here. Means this equals to alpha partial mu delta phi plus alpha partial m partial okay. You see, what I'm doing here is this term is this term, okay? This term is this term, and this term there is one derivative acting on this one, okay? I choose to combine with another term to form a total derivative, okay? Total derivative, and then I have to subtract another derivative acting on the first, okay, without touch the second. But the point is that term can combine with this term, okay, to form this bracket. So as you can see, the guy inside of this bracket is what? That's the equation motion. That's right. This is nothing but the equation motion. Okay. So if you use the equation motion, this is gone. Okay. This equals to 0. If you impose equation motion, this equals to 0. Then you only get this term. Only get this term. Okay. This is just to follow the if you change your field, then how the action should be changed. To follow that one. Now, demanding this is a symmetry, we also know this will always change in this way. And this has to be equal to this one, okay? Then demanding the symmetry. The symmetry means that if this is a symmetry, if this is a transformation on a symmetry transformation, then this has to be equal to alpha partial mu J mu. Clear? That's one, okay? That's my this one. Now you get some equation. After imposing equation motion, you get this term equal to this term. Okay? Then alpha dropped. Alpha as a parameter dropped, okay? So you get some derivative equals to another derivative, you see? If this derivative equals to this derivative, you cannot guarantee this object inside are equal, right? But instead, you can redefine another object that must be conserved. For example, you can define the current. By definition, I can define this current as a partial L, partial mu, delta phi minus capital J. It's trivial exercise, you see. Because I have this one equal to this one. I just combine this one minus this J mu. I get another one. Then immediately, out of this definition, I can get a partial J mu equal to 0. See? It's trivial, right?
还是被那个是讲大。
Okay. Sorry for that's an important equation. Yeah, it's not complicated. So Luther's theorem can be derived very easily, but you have to be careful what you're doing. So here we basically use the definition of the symmetry. Okay, we impose also equation motion. Okay, then we claim that there always exists a J mu. Okay, J mu should be expressed in this way, and the point is J mu is always conserved. This is just a result of my derivation calculation. Here, use this term and this term.
But I wonder how can we derive a capital J mu because it seems 我说中文吧，我不太懂这个大写的 J mu，那我该比如说我现在有个对称性出来，我该怎么确定这个大写的 J mu 是个什么呢？这样子我不是才能确定有个小写 J mu。
I will show you one example. Where is it? How to do it? Yes.
J arbitrary。
Okay.
大写的这个 J 是任取的，对，我跟它差不多，就是说它是否可以说是一个任取的东西？
No.
不是吧？
How to determine
Can be
the capital J?
Yes.
How to determine the capital J?
Yeah. All these three are. I will show you. If you can tell me explicitly which is symmetry transformation, I can tell you what is general. We will show this one very soon.
What if sometimes if we perform an infinitesimal transformation with more than one infinitesimal perimeter, and how can we, for example, have alpha 1, alpha 2, and how can we formulate this?
Just one by one.
So
With each independent infinitesimal.
do we need sum over all alpha
Yes.
labels of alpha?
Yes. Any other question? That's very good questions. Yeah, these are very important questions about this. How to calculate the capital J mu? That's a very important question. We will illustrate this as for examples in particular examples. Any other question about the derivation? Just the 2 lines derivation of the Löder's theorem, but it's extremely important.
Does the invariation of the S implies that we send the Lagrangian must to the 算我说中文吧，那就是 S 的那个是 invariant， 是不是必须得保证这个是那个是 L 必须得那个是变成这样的一个形式？
That's right. That's what I mean by at most. Yes.
但是好像没有证明啊。
是一个边界条件。
No, yeah.
和朗道力学里面那个是一样的，你那个是差一个时间的全导。
This is a mathematical fact.
全导。
If you don't want to change your integral,
这是应该是没有。
at most your integrand can change by total derivative with a trivial boundary condition. That's it. Any other question?
Is it guaranteed that J mu is vanishing on boundary?
Which J? I have 2 J.
The big J.
Big J. Sorry, say it again. Big J can be 0, yes.
Is it guaranteed that it is vanishing at any point of the boundary? Safely.
That's a good question. I think so. Yes, that's what we mean by trivial boundary condition. That's right. So with this integral, since this is the total derivative, you turn to some surface terms for this J, okay? Meaning that you only evaluate the J at the endpoint or boundaries, okay? The point is we always, quite often, we impose that's trivial. That's zero.
But I think it's also okay if the action 差一个就单纯差一个常数应该是没有关系吧？就是 J mu 也不一定要完全 vanish 吧？就是它只要你在边界上面计算它是一个确定的一个常数，那应该也是没有问题的吧？
那就变了。
Following this, my definition, Yeah, observed consistent with I define the symmetry, just say S is the invariant. This is my definition.
你要变成常数的话，它就变了。
Okay, any other questions, comments? These are very interesting questions and discussions. Yeah, as asked, this is a little bit schematic, too formal. Okay? Show some formulas, give a very strong claim. You may feel uncomfortable, okay, without doing exercise or examples. So let's do it. So as I said, the simplest example is say this J is just trivial. If the symmetry can preserve this L, also then of course preserve S, okay, which means this is zero. This is zero. Indeed, we have some such examples. Okay, which example leave this L invariant? You know, U1 symmetry, right? For example, internal symmetry always preserve the Lagrange. Okay. What do we mean by internal symmetry? Internal symmetry means those symmetry distinguished from the space-time, does not touch space-time. Okay, internal. That's what we mean by internal. Okay. So examples. For example, let's consider U1. Okay, then L is some. We can say this is a free complex scalar. Okay, free complex scalar. Lagrange. Okay. Here I use a norm. I use a norm squared. It just means phi and phi star. Okay, phi and phi star. There. You can use another more precise form. You can expand this in terms of phi and phi star, but the same thing. The point is, this is invariant famously, this is invariant under internal U1 symmetry, which means that if your symmetry send phi to a phase rotation with e to the I alpha is a constant, okay, phi. If you multiply by a phase factor, okay, e to the I alpha, you can easily check this is invariant, okay. You see, if there's the phi, there's also phi star. Phi star is complex conjugate of phi, okay. Then when phi rotate under this e to the I alpha, phi star will rotate under e to the minus I alpha, okay. Then we multiply them together, two phase cancel. Okay, that's the reason the complex together belong to the invariant on the phase rotation. Then, but you have to be a little bit careful. Okay, just a few remarks. You can express this effect more precisely using phi and phi star. Of course, you can also choose another way to represent this, because the complex of phi can always be deconstructed or composed as two real scalars. Okay, you see, two real scalars. Right? You can choose either this way or this way. Okay, okay. But you have to pay a little bit of attention. When you choose this way, you have to find phi star independent variables. Don't confuse. Okay. If you choose it this way, also you have to view the phi 1 and phi 2 are independent variables. Okay. Clear? But that's the same thing. The point is, for infinitesimal transformation, now this transformation is so simple. Okay, it's not even fancy in this way. This is so simple. So you can write explicitly what is the infinitesimal transformation for this one. Okay, which just means I choose a very, very small parameter. Alpha is small. Okay, when alpha is small, you can do Taylor expansion. You see, look, and you can write the that form. You can work out the infinitesimal transformation, for example, if alpha is small, we will get alpha delta phi, which we defined there, explicitly equals to, in this way, alpha I phi. And also alpha delta phi star, I choose to use this one, phi star. Then this is minus I phi star. You see? So that delta is not so scary, okay? In the explicit example, this can be always worked out, okay? We can treat this delta explicitly. So this is one rotation. How this delta looks like. Okay, it's just equal to this one. You can easily do this more parameter expansion for this transformation. Then let's just follow this result. The point is that I wish I can, I wish I want to I want to work on this one, right? But said this U1 rotation preserve L, so this J part is trivial. J part is trivial, only the first part left, okay? Only the first term in this conserved current. So only the first term left. So what is the first term? So the first term is nothing but the two piece. As said, which is mu phi star are independent. So there are two piece. And we also know what is delta phi star. So just plug in, work it out. This will be equal to I partial mu phi star phi minus phi star. Wow. Okay. Now, if you are not sure about this conservation, you can easily check it there. Because I have a explicit form for J mu. You can check whether it's conserved or not. You can check it. So indeed, if you check it, you get the partial mu J mu. In this case, will be equal to, let's say, I want to calculate partial mu J mu. I have a J mu. Okay. Yeah, I have J mu. This one. I want to calculate this one. Okay, to act this partial mu on this bracket. Okay. Then for the first term, two parts, right? For this one, I get a partial mu phi star, which is a box phi star. Okay, times phi. Then the second term plus partial mu phi star partial mu phi. Okay. Okay, because these are time together in derivative for this total. Also, for this one, you have two terms. Now, the cross term cancel. Okay, phi star term cancel because of the minus sign. Then the only thing left over is the box phi star times phi and the box phi times phi star. Okay. So that's the main result. So result is the box phi star phi minus phi star box phi. And as you can see, if you impose the equation motion, this has to be zero. You see, right? Because equation motion guaranteed that the box is zero. Okay, zero for both. So this has to be zero after you impose the equation motion. Okay. Okay. So we checked perfectly. Okay. In this case, even though in this case does not touch the question asked there. We'll go with that question in the next example. Okay. So this is a simple exercise you can do for the internal U1 symmetry. Indeed, there is a conserved current, which can be derived very easily. Okay. Now, what next? Very familiar here. Well, next example, we're going to look at is one of the space-time symmetry. which is actually very important, which is the translation. That's the U1 rotation, right? And this is the translation. Translation is a part of space-time symmetry. Okay. Okay. Now the point is, if I have my fields, if this is my just to give some picture to you guys how to think about it. What do I mean by act translation of my fields? What does it mean? Okay. It means, suppose this is my field, for example, my field is a very simple one variable function, okay? Just picture-wise. And translation means translation along x, of course. But now the point is here, I'm not talking about the coordinate transformation. I'm not really talking about translate my fields, okay? Which means that you can think about the x is fixed. The coordinates are fixed, but the fields are moved some way. So it's a very bad drawing. I really transform my fields, okay? So in this translation, so I really translate my fields, meaning I move my fields along the x direction. So in that context, you can really work out, for example, your field by x, they really transform. They really transform into, following this one, some other one, because this is the infinitesimal amount. For example, if you focus here, you x, you focus on position x, then after the transformation, you get some new field value. This is the previous field value. If this is the infinitesimal amount, then the difference is also very small. Okay, difference is very, very small. Okay, that's essentially this piece. Essentially, this piece. This piece in this translation, this piece can be expressed as a small parameter alpha mu partial mu by x. Okay. So that's the form how translation acts on the field. So I have a funny index mu here, because in space-time there are different directions. Okay. You put a mu index to label which direction you are talking about. I have 4 directions in space-time. So mu denotes which direction. And this is a small parameter. Now you're saying, okay, why promote your small parameter into a kind of vector? That's fine. That's just because I have given choice of directions. Now, this is the general form. This is the general form how translation acts on a scalar field. On a scalar field. Okay. Afterwards, after this class, you can try to justify yourself or derive this one. Why this makes sense? Why this is correct? Okay. You can find a different way to derive this one. Okay. If you are worried about this particular form. I'm telling you this is perfectly correct, and now since Lagrangian is also a scalar, okay. So as I said, Lagrangian density, the index has to be contracted over, right? Whenever the index is contracted over, when the index contracted over, then we view it as a scalar. So L itself is also a scalar. Which means under this translation, L has to be transformed in this way. See? because all the scalar have to be transformed this way. So L is a scalar. So this is one example to make this capital J clear. No? See? So when you do translation, moving in space-time along some direction, then you can work out this capital J explicitly. And the capital J. Because capital J comes from this transformation of the Lagrangian. Okay. This is perfectly a total derivative, you see? So in this case, J is L. Okay. Well, we already know what is J. Now, on the other hand, we have some other piece, right? We also have this piece. This part we can also work it out. Right? Because we know delta phi, we know this one, so we know this box. And we can get a conserved current in this case. So let me erase this. Oh, we don't need that. So now the conserved current becomes, as said, there are two terms. We use some two index. I will explain why there appears two index. Mu equals 2 partial L partial U partial U 1 x minus G mu L. Okay, now the why there's looks a little complicated than before. Before you only have a J mu. The point is, in this case, alpha is a number, it's a parameter, it's not a vector. Okay. Now I promote the alpha as a vector. I introduce another index. Okay, but don't confuse. This index is introduced in order to make this contraction. Okay, nowhere else. So that mu is not quite this mu. Okay, they're different index. Okay, there are different indices. So it's not quite this one. In order to distinguish it, it's actually better to put this as a new. The same thing. Okay, just want to say these are two different indices. Okay. Now, if you want, I can further write this term into alpha nu partial nu. I want to use this matrix to contract or lower down the indices. Okay, I can choose to write it this way, but that's the same thing. No, not big deal. Okay, you see. You see why we want to do this? Because I want to match this index with this J mu. This is J mu. So that mu is this mu. Okay, I want to. I use the same notation. Okay, is that clear? Then what? Then I work out both two terms. Now, in this delta phi, there's another index nu. In the delta phi, there's another index nu. It's perfectly okay because it's nothing but this nu, right? Because this nu was introduced in this delta phi. Okay. Delta phi, the formation delta phi now promoted with the index nu. Okay. So there's a new index appeared here. Now, after I write this object into this form, meaning I want to match this mu index with this mu. They're the same mu, okay? Now I can pick out this my J mu. Where is my J mu? My J mu is just this part, okay? This part. So as I said, total current equals to the first term and the second term. Second term is the J mu, is in the bracket. Okay, good. So complicate in one short word. The point is, in this current, you have to stick to mu index. So if you only focus mu index, it's a current, fine. It's a perfectly defined current, okay? But the point is the object itself carry another indices, but that's okay. It's just the object is more complicated than before, okay? You can, for some reason, for some purpose, you can forget about or don't pay too much attention to this another index. It's just this index was invented to complexify the object. This index is the original current mu indexes, okay? That's what happens. So this is a perfectly okay conserved current because this is a famous object. It's a stress tensor, stress energy tensor. Do you know what is the stress energy tensor? Do you know that before? Yes.
就是零零项是能量，后面第一行第一列都是动量，剩下都是那个应力。
Very good. Very good. I think you already heard about this stress energy tensor a lot from different subjects like fluid dynamics, solid physics, whatever. But this is the field theory version of that. Okay. In particular, field theory tells you that stress tensor is the conserved current for space-time translation symmetry. Okay. What is the translation symmetry? Translation symmetry essentially means every point is the same. Okay. There's no difference between this campus, Handan campus, and the Jiangwan campus. If you do the experiment here, it's the same as doing the experiment there. But there's a translation symmetry. Okay. What do I mean by translation symmetry? Now, following this symmetry consequence, following in particular Loeder's theorem, translation symmetry predicts the conserved current, which is nothing but a stress tensor. So that's the field theory definition of the stress tensor.
有个问题，但是我们知道能动张量它应该要是对称的。那我这里推导出来的这个 T mu nu，我给它降指标降下去了之后呢，能保证它一定是对称的吗？可以证明吗
Metric is diagonal. 放一个符号就可以。Okay. Any other question for these two examples? The second example in particular illustrates how to specify this capital J mu for some particular symmetry. Okay, that's the point. Now the last 2 minutes, let's go to the also important consequence of this other current, which is the conservation law. So we're saying this current is conserved. But come on, conservation. What we learn in high school, conservation originally means something does not change as time goes by. Doing the conservation. That's the conservation. So how to relate that equation with our middle school understanding of conservation? Okay, which quantity is really conserved? That's the question. So indeed, there is a physical quantity called conserved charge. Is conserved. So what is conserved charge? Conserved charge is some space integral of this J naught x. So we have J mu, right? Let's pick up the zero component of that J mu, okay? And do the space integral. Only space integral, okay? Then you get Q. This is the charge, okay? Make sense? Why? Because J naught is the charge density. If you integrate charge density over space, then you get charge. So why this is conserved? Easily check. partial TQ is equal to this one. Also, now I plug in this T derivative to here. The same thing. This one. Now, by this partial mu j mu equals to 0 condition, I can translate this partial 0 j0 into a partial x, right? J. Right? Because this equation pairs this one to this one. Now I have a space derivative with a space integral. As you can see, the trivial boundary condition guarantee this is 0. Okay. Because this is the total derivative in space. You see. So this is 0. So get 0, we justify the time derivative of this quantity is 0, which means this quantity does not change as time goes by. Okay. So Q is really conserved. So Q is called the conserved part. It's a very important quantity. Now in quantum mechanics or in quantum field theory, we're going to push later. Q is a conserved operator. It's an extremely important operator. Okay? Because Q measures all the charge. Okay? In quantum mechanics, if you want to measure some charge on some states, what is the charge this state carry? So you have to evaluate this Q operator. Because Q operator does the job. It's the charge operator. The charge operator. Okay. Let's stop here.
天天喜欢
那你光会觉得你
这边这个两者这个就
这里找的大写谁的话，
你就把这个派这个
是如果是类比这个信也不要概率这个
这个位置，然后找一个更复杂的东西，该怎么找？对，除了这两个，因为它这两个，这个是这个方。
真正的理解哪一个是
也就是
因为你现在不知道什么问题，是因为你没有稳健错，你看知道你在说哪个？
就你可以，我觉得就是从这个错误。
然后这边这个东西，
所以说也就是我知道了，比如说把这个数据的新闻
是可以导写最后还有它的灵感就是它两个是就那个，因为这个我算是不搞的，S 别人方便因为。到哪去？
教程序版是真的
这样打的，
第二首是啊 ，sorry， 这 U1 别人还提到了，
还有这个他说了2份，他知道，还有一个就是
意思在这说明那个那个叫什么北那个叫什么还有那个什么学的两分赛期待
就是过类的。因为他要买你没有听过历史，你不是我他妈殖民路这个看到这个我们画了一张，这里是那个卡丁里面那个还可以上下哪个都是一，然后呢，这个打上下哪个都会死，一这个意思，我两个都死，两个。
如果跟一般的一些，
他用刚刚没了，对，我只有10年的吧。
我这里拉开它，
下个就
再讲2个例子，一个是内部转动，
那这边其实
打哪个德贵斯应该来试一下飞销，非常好。
之后我们担心了，好吧？
谢谢。
你 C 嘛？哇。
这两个情况下，我们
我想问你一下，在过脑后多
因为全趴了，
我知道。
他
看到了，
哎，我下午要去了，
我知道，
没事没事，
对啊，在上比较像。
就是很回来，
哦，那我
下来，
我就是对这个上了。
你下来，因为你没有什么